What if you have now an electron encountering an anti-electron or anti-electron? What do you prefer, anti or anti?
Positron.
Proton or anti-proton?
Anti.
You prefer the anti? Okay, cool. So, what if an electron meets a positron? Then, because the positron is antimatter and the electron is matter, then they completely annihilate. And I guess if I say annihilate, I shouldn't say completely. It would be redundant to say, I mean, to annihilate means it's not like destroyed. Like you can destroy something and break it into pieces. You still have pieces in there. This is like they completely disappear. I mean, you don't have any mass in there. All of that mass just gets converted to radiant energy. Energy. Right? So it's like that's what annihilation means in this context. And so if an electron meets an anti-electron, which once the positron is, or the anti-electron or positron, once it is produced very soon, I mean, we live in a world filled with matter, it's going to find an electron and then they'll annihilate. If you go to the frame of reference of these two particles where they are both at rest, what is the total initial momentum? What if they're both at rest? What is their initial momentum? Zero. So then they annihilate, and so whatever you have at the end, the total linear momentum of that has to be zero from conservation of linear momentum. So if for example you say that the electron and the anti-electron or the positron, right, they annihilate, and you go to the frame of reference of when, you know, to the center of mass of both of them where they're at rest, let's say, then total initial momentum is zero. And if you say that only one photon is created, well, the photon is going to be traveling at the speed of light. And the momentum of a photon is not zero. Never. Zero. Because the expression that relates the energy of a photon to its momentum is but the mass of a photon is zero. So for a photon, well, it's just that. And for a photon, P is H over lambda. And so a photon has a wavelength associated with it. It's got a frequency associated with it. It travels at the speed of light. So a photon always has momentum. So if you just say that the electron and positron annihilate one another and initially the total momentum is zero, and you just say there's only one photon, then you don't have conservation of linear momentum taking place. Because one photon is not going to have zero momentum. Whereas both of them, if you go to the frame of reference where they are at rest, then you can have zero momentum. So what must happen, and this is always observed in the laboratory, is that two photons are produced. And because the two photons must have a total linear momentum of zero, because that's what you had in the beginning, right? That means that these two photons, the only way for two vectors to add up to zero is if they point in opposite directions and they have to have the same magnitude. Right? That's the only way for two vectors. A momentum vector added to another momentum vector, if you want them to add up to zero, only two of them, they have to be in opposite directions and of the same magnitude. So therefore, you have, let's say, a photon, let's say, going to the right. If you draw that, then you're going to have a photon going to the left. Let's say P is the momentum of this photon, P1 is the momentum of this photon, P2 is the momentum of that photon. You can think of that, that's a nu. Nu, it's a Greek letter, nu, that means frequency. This is just from another textbook. So you can call this HF1 and HF2. So in that process, what you have is, let's say, an electron and a positron at rest. At rest. That's the mass, that's the mass. So that's before. So the total linear momentum over here is 0. So if at the end you say that only one photon is produced, let's say this way, so photon number 1, right, with momentum p, then this is after. If the momentum of this can be 0, the total momentum of this will be, you can think of this as hc over lambda, right? I mean, I'm kind of going in circles over here. We have that. But also, E equals hf or hc over lambda for a photon, right? Max Planck wrote this. So if I equate this to this, which comes from relativity, and this one here was from Max Planck, if I equate this to this, then I get that Pc is equal to hc over lambda. The c's cancel, and you get that the linear momentum of a photon is h over lambda. That's a photon, gamma. So this one is going to have a lambda 1, for example, and this momentum will be h over lambda 1. But that's not equal to 0. And so if you just say that the two particles, the particle and antiparticle annihilated one another, and it just resulted in one photon, then you don't have conservation of linear momentum. So what must happen is that since the total initial momentum was 0, it has to be 0 at the end. And this is always observed. There's another photon made over here. So photon number 2. And then let's call this lambda 2. And the linear momentum of this will be P2, which is h over lambda 2. But the total linear momentum here will be the linear momentum of photon number 1 plus the linear momentum of photon number 2. But because this has to be 0, right? That means that P1 plus P2, the sum of these two momentum vectors has to be 0, which means that the linear momentum of photon number 2 has to be equal to the negative of the linear momentum of photon number 1. Well, the minus sign is because that makes sense because they're going in opposite directions, or it tells me that they have to be traveling in opposite directions. But what about the magnitudes? If I set up the magnitudes equal to one another, because the only way for two vectors to add up to 0 is if they point in opposite directions and they have the same magnitude, so this would be h over lambda 2, and this would be h over lambda 1. So the h's cancel, so lambda 1 must be equal to lambda 2. So the two photons that get emitted must have the same frequency, must have the same wavelength, they must have the same energy. And if I write down now the energy equation, so this is number 2, or B, what is this? Pair annihilation. This is conservation of energy. If I write down conservation of, I'm sorry, that was conservation of momentum. If I write down conservation of energy, for that process, what do we have? Well, at first we had two particles, right, at rest. So the total energy was what? It was mc squared for one of them and mc squared for the other one. They were both at rest, no kinetic energies, because I went to the frame of reference where they were at rest. And then at the end, what do you have? You have the energy of this photon plus the energy of the other photon, which is hc over lambda 1 plus hc over lambda 2, but lambda 1 equals lambda 2, I'll just define that as lambda. So this is 2 hc over lambda, and this is 2 mc squared, so the 2's cancel, and I get that essentially it's like this. I like to think of it like this. I like to think that this photon, I mean this particle here, turned into this photon, and the other particle with the same mass, so it is the antiparticle, or the antiparticle, made the other one. But it's really, they can't make, they have to annihilate together, it's not like you have one particle that turns into energy right away. So in the previous formula, we had a 2 in here. Now we don't have a 2, because in the previous formula, we had radiation turning into the particle-antiparticle. But in the reverse process, right, the pair annihilation, the two particles annihilate, and they don't make up one, they don't turn into one photon, they turn into two photons. For arguments, for reasons of conservation of total linear momentum. And this is what's observed in laboratories. Yes?
Over there, it's P2 equals negative P1, and then the bottom, where's the negative sign?
So what this means is that if I write a mathematical expression like this, mathematically, what is that telling me? That they are opposite in directions, but their magnitudes have to be the same as well. So that tells me, so the minus sign means that they are in opposite directions. The two vectors, P1 and P2, are in opposite directions. That's one of the messages, but the other message is that the magnitude of P1 is equal to the magnitude of P2. So that's, if I write down the magnitude of P1 equal to the magnitude of P2, the magnitude of P1 is this. Actually, that's for P2 and this one for P1. So this would be h over lambda 1 equals h over lambda 2. And you see that quite a bit when you learn about action-reaction pairs of forces. So in Physics 185, when do you learn about Newton's third law? Probably chapter 4. Here it is. See that formula right there? A vector equals the negative of another vector, right? So the case here is this. This is the force that Arnold exerts on the ball. So let's say this is my foot, and I kick the soccer ball that way. Now the question is, what is the force that the ball exerts on my foot? Well, the relationship between these two forces, the one that I exert on the ball and the force that the ball exerts on my foot, right? These two forces are related by this equation. And what this equation is saying is that the minus sign means that if I kick the ball that way, the ball hits my foot in exactly the opposite direction. And if I kick it with a force of 10 pounds, the ball hits my foot with a force of 10 pounds. So this vector equation over here means that the two vectors point in opposite directions and have the same magnitude. So the minus sign tells me that they are in opposite directions, but that expression also tells me that their magnitudes are the same. And that's what I did over here. They point in opposite directions, but that means that their magnitudes have to be the same. Because the only way for two vectors to add up to 0, if I tell you, this vector acts on this, let's say it's a force vector. This force vector over here is, 10 newtons that way at 30 degrees above the horizontal. What is the other force that has to be acting on that object so that the sum of the forces is 0? So it's got to be opposite to that, and also 10 newtons. And then they'll add up to 0. Otherwise, they're never going to add up to 0. So that's kind of what I used for there. So again, this is not a formula that I go around memorizing. You know, I just think of the process, and then from there I write this, and then I get the answer. Now, I wanted to say something about the Doppler effect for light, for electromagnetic waves. You learned about the Doppler effect for sound in Phys 185. And in Phys 185, you talk about sound waves. And then over there, you are concerned with the speed of the source of the sound. You're concerned with the speed of the sound itself, and also the speed of the listener of the sound. There are three speeds that you need to keep track of: the speed of the source of the sound, the speed of the listener of the sound, and the speed of the sound itself. And two frequencies: the frequency of the sound that's emitted by the source, and the frequency of the sound that's heard by the listener. Two frequencies: whatever the source produces, the frequency over there, and whatever the listener hears. And three speeds, right? So in the case of light, you still have the two frequencies, which is the frequency of the light emitted by the source, and the frequency of the light that's observed, if it's visible, or picked up, or received by the receiver. Right? But then you only talk about two speeds, or two speeds: the speed of the light itself, which is the wave, and instead of the speed of the source and the speed of the observer, it's the relative speed between them. It's only one speed. So, you know, in the case of sound, so this is the Doppler effect for sound. So you have, let's say the frequency of the listener, right, is equal to the speed of the sound plus or minus the speed of the listener divided by the speed of the sound plus or minus the speed of the source of the sound times the frequency of the sound. So you have something like this. I mean, I like to write this other numerator down here, right? But you have four possibilities over here. You can have plus plus, or minus minus, or plus minus, or minus plus. Right? So v is the speed of the wave itself, of the sound wave. But in the case of the Doppler, and then you learn about a reference direction. In the case of sound waves, the Doppler effect for sound, the positive reference direction is always taken from the listener to the source. In the case of the Doppler effect for radiation or for light, in that case, this is the frequency that's, well, it's not listened, it's not picked up. Sound, you can hear sound, but light, you don't hear light. You observe light if it's in the visible spectrum. So oftentimes this is or received. And then you have the frequency of the source. But then what you have over here is the following. Either you have this case where you have a square root over here, and then you have C minus V, or C plus V. That's one case. Or the other case is F of, the frequency of the light that's received is the frequency of the light that's emitted by the source, and then you have a square root, and then it's C plus and C minus. Where V is the relative speed between the source and the receiver of the radiation or of the light. I mean, light usually means if you can observe it in the visible. Radiation is general. Radio waves, microwaves are radiations, right? But sometimes people use the word light, but light is really usually more for the visible region of the spectrum. So you either have this case or this case, and C is of course the speed of the light, the speed of the wave. So I prefer to write the Doppler effect like this. And then C over here represents the speed of sound, the speed of the wave. And C over here, this is the speed of the wave, but in this case it's light. So here, in this context here, C is the speed of light, the wave, which is the wave. And in this context over here, C is the speed of the sound in the medium, which is the wave, right? And then the V's deal with speeds of the listener and of the sound, the source of the sound, and for the case of light, it's the relative speed between them. Now you only get two choices. In the case of the Doppler effect for sound, it's a little bit more complicated because you have four possibilities for the signs. You can have plus plus, minus minus, plus minus, minus plus. There are four possibilities depending on which way the source and the listener are moving, right? In the case of light, if the numerator is a minus, then the denominator is a plus. If the numerator is a plus, then the denominator is a minus. This is the frequency of the light produced by the source. So the S here means source. And R, this is the frequency of the light that's picked up by the receiver. That's received by whoever, or observed if it's somebody observing the light. Now, in this case number one, which of these two frequencies is higher? From just looking at the mathematics of this expression, which of these two frequencies is higher? The frequency of the light emitted by the source, or the frequency of the light picked up by the receiver? Which is the higher frequency?
The source.
The frequency of the light emitted by the source. So therefore, the frequency received is less than the frequency emitted by the source. Therefore, what must be happening to the source? Would it be moving? If you pick up a frequency of light that's smaller than the frequency that is being emitted, is that source moving away from you or towards you if what you pick up is smaller? It's moving away, right? So in this case, the source is receding from the observer. We don't say the listener because you don't listen to light. You can observe it, but not listen to it. So in this case, and if the frequency that you pick up is smaller than the frequency of the light that is being emitted, would smaller frequency take you towards the red end of the spectrum, of the visible spectrum, or would it take you towards the blue end or violet end of the visible spectrum? Lower frequencies, would it be for red or blue?
Red.
Red. So then this one, in this case, if the source of the light is receding, moving away, the frequency that you pick up, so then this is associated with what's called a redshift. So this is when the source moves away from the observer. And this one, if you analyze this one, if you compare the frequency of the light emitted by the source and the frequency of the light that is picked up by the receiver will be picking up a higher frequencies, right, than what the source is actually emitting. So in that case, the source has to be approaching the receiver, and it's a higher end in frequency, so this is a blue shift. So when people talk about a blue shift, it means that the frequency of the wave that is received, picked up, detected, heard, observed, right, is higher than the frequency that was actually emitted by the source of the wave. So this happens, you get a higher frequency when the source is approaching you. So here, this happens when the source approaches the observer or receiver. So I actually wrote it with, notice that in this case, because the plus and the minus, the frequency that's picked up is actually higher, so it's a blue shift. I wrote it in blue. And in this case, minus sign in the numerator, plus sign, so this frequency picked up by the receiver is smaller, so redshift. I color coded it. And what happens if the speeds of here involved, the relative speed between the source and the listener is much less than the speed of light in vacuum? I mean, you might say, well, you know, if this is very small and that's very small, then you can forget about them. So C minus nothing, C plus nothing is like C over C is 1, and then the two frequencies are the same. That's at the extreme. Same thing over here. But what if this is, you know, let's consider the first order correction. And so there was a homework problem. Can I erase, maybe I'll just erase this, where I've done that calculation. So what we're gonna do, use the redshift or the blue shift? Big one.
The blue.
Blue it is. So I'm gonna use this. This would be f of s, and then we have the square root of c plus v, c minus v, right? I can write this as f of s. Oh, maybe let me just use another line. And I can write this as c plus v to the 1/2 and c minus v to the 1/2, right? And I can factor out a c. So I'll say this is c. And then, well, I have a 1/2 and a 1/2, right? So how about I do this? C, and then I have 1 plus v over c, and c, and this is 1 minus v over c. Correct? I can put the 1/2, and then this cancels that. So then I have f of s, and then I can write this as 1 plus v over c, and that's in the numerator, so this is plus 1/2. Now this one that's in the denominator, I'm going to bring it upstairs. So then this becomes 1 minus v over c minus, raised to the minus 1/2. Right? Are you happy? And then the question is this. What if v is much less than c, so that this ratio, v over c, is much less than 1? What if we have that? Then you thought you were going to be done with this, right? So we have from math what? 1 plus x to the nth power. It's 1 plus nx plus n minus 1 over 2 factorial x squared plus n minus 1, n minus 2. I'm telling you, this thing shows up so many times. And this is true for x being positive or negative, right? But being much less than 1. So since this is much less than 1, since this number x is much less than this factor, and that's what we have over here, v over c is much less than 1, v over c is much less than 1, then we approximate 1 plus x to the n simply as 1 plus nx, and we're going to throw this away, and we're going to throw all those terms away. So that's an approximation. So that means that this becomes f of s. Now, the first one, notice this approximation here is 1 plus the exponent times the small thing. So this would be 1 plus the exponent, which is 1/2, times the small thing, which is v over c, plus other terms that I'm going to drop away. And then the second factor is 1 plus the small thing, which is minus v over c, times the exponent, which is minus 1/2, plus other factors that I throw away. So now this is an approximation because I have a lot of other factors in there. And if I multiply through, I'm gonna, well, the two brackets here, so this would be 1 times 1 is 1, and then 1 times this. Now this minus and this minus cancel, so it'll be 1 times 1/2 of V over C. So it'll be plus V over C 1/2. And then when I multiply this by this, I'm gonna get another plus V over 2C. And then when I multiply this by this one, I'm gonna get plus 1/2, and 1/2 is 1/4. And then V over C is V over C squared, plus other terms. And if I compare these terms, the V over C squared is much smaller than V over C. So I'm gonna throw this out, and so this approximates to f of s, 1 plus, and then I have 1/2 plus 1/2 is 1, so it's V over C. So this is the approximation. So I have that in my notes. I just did it for you, but in my notes it says, one can show in problem 78 of chapter 16 actually of the textbook, that when, or maybe that's a 30, no, that should be a 36, no, well, maybe that's the problem, that when V is much less than C, you get this. So I just did the blue shift. So with the blue shift, you get a positive sign because the frequency received is supposed to be higher than the frequency of the wave of the light emitted. So with the plus sign, you get a blue shift, and with the minus sign, you're going to get a smaller frequency, so it'll be for the red shift. So if I had done this for the red shift, this plus would have changed to a minus, this minus to a plus, and if I did this, the only difference would be this sign over here. So when is this useful? When is V much less than C? When cops want to know if you're speeding. Right? Cop is on a motorcycle at rest, takes out the radar gun. You are coming in your car. It shoots the radio waves, electromagnetic waves. Right? It shoots the electromagnetic waves that travel at the speed C, right? And then they go to your car, boom. So they know the frequency of the radio waves that are being emitted by the gun, right? It goes to your car, it bounces off the car in various directions. Some of that comes back, but it comes back shifted in frequency. So then it measures the frequency of the waves that come back. It knows the frequency of the waves that were emitted, and then virtually then the cop can figure out what's the speed of your car, which is very small compared to the speed of light. So this problem, actually the problem, I don't know, maybe I think there's a homework problem where I did it for the, radio waves. That problem really consists of two parts. The cop has the radar gun, which is the source, and then the car is the receiver. So just calculate the frequency of the radio waves that the car receives. And whatever that frequency is, now think of that as the source, and then the cop is the receiver. So you really have two Doppler effect problems in there, and then the cop can figure out how fast you're traveling. All of this is automated, and very quickly it tells him it converts it to miles an hour, and depending on the speed limit in that area, then the cop can decide to either give you a ticket or not give you a ticket. But it's just a Doppler effect for radio waves, which is, a light wave, right? But that's how that works. And the last picture that I have over here is really cute, I think. The idea is the following. The idea is the following. So Albert Einstein made corrections to the theory of gravity that was enunciated first by Isaac Newton. Newton said that the gravitational force that one object with mass exerts on another object with mass is a constant, universal constant, which has the same value everywhere in the universe. That's why it's called the universal gravitational constant, capital G. Then you multiply the mass of one of the objects by the mass of the other object, and then you divide by the square of the distance between the center of mass of one object to the center of mass of the other object. Right? But inherent in that expression is that gravitational forces are exerted and experienced only by objects that have mass. So, this was Newton. When you consider a beam of light, like light coming from a star to the earth, right? Then light are photons, right? You can think of light as a stream of particles where each particle, each quantum of the light is a photon with zero mass. So if the mass of light, of radiation is zero, then using Newton's theory of gravity, they should not interact. It should not interact with objects that have mass. Right? They should not experience the gravitational force. But what Einstein discovered is that a beam of light can be deflected by the presence of the sun, for example, something that has a lot of mass. And so, in other words, Einstein was saying, well, light, even though it doesn't have mass, its path in space would be affected by the presence of the amount of energy that the sun has. Because of its big mass, got a lot of energy. And so what Einstein said is that the force of gravity is really an illusion. It is really an illusion. What happens is that the presence of matter and energy, a lot of matter, it's a lot of energy, right? It curves the space around it. It warps the space around it. So in this picture over here, think of space as a two-dimensional world. Just two dimensions, like the surface of your bed. Let's say it's flat, right? Now, but by putting the sun in this space, right, with a lot of mass, which has a lot of energy, that presence of the sun warps the space around it. And so if you have a star far away, shining light that then is picked up by the earth, right? But let's say that light coming from the star follows this path, right? Well, because of the curved space around the sun, because of its huge matter energy content, then the light will follow a path like this and go to the earth. Now, we on earth, we think that the light, if we see the star over there, we should not be thinking that the star is over there, right? To us, if I see the star over there, right, then it's because to us, the light is coming straight to our eyes from here. So to us, we think that the star is here, when in fact the star is over there. I think we talked about this as in terms of the refraction of light of sunlight caused by the atmosphere. We argued that when you see the sun, it's about to begin setting, the fact is that it's already over the horizon, right? So to us, we think of the light as traveling straight from the star to us. So we think the star is over here when in reality it might be over there. Now in this picture, this is an exaggeration. But Albert Einstein, using his equations of general relativity that he enunciated in 1915, he was able to predict what this angle should be. And it's a small angle. It's a ridiculously small angle, but with accurate equipment, you can measure it. And so, in the next time that there was a solar eclipse, which was I think like 3-4 years later, 1919 or so, then the observations were made by a couple of groups, one in Africa, one somewhere else, I don't remember where, and they measured this angle, and it came out to what Einstein predicted. So why do the planets orbit around the sun? So what we teach in 185, Physics 185 is, right? Oh, okay. So what we teach in Physics 185 is that the sun has mass and it exerts a gravitational force on the earth and pulls it, and the earth is moving, so then it gets pulled this way, so then it turns, gets pulled, it turns, gets pulled, it turns. Luckily for us, the earth is moving like at 20 miles per second on average, so it keeps missing falling into the sun. And each time it goes around, we call it a year, right? But what Einstein said was, well, what's really happening is that the sun is not really pulling on the earth. What the sun is doing is it's curving the space that the earth is moving in. So imagine if the geometry here were such that the earth were moving, and it just kept on moving around the sun because of the curvature of the space. And that is what Einstein argued, that really that, force of gravity as envisioned by Newton is really more of an illusion. What's really happening is that the presence of matter and energy warps the space, it bends the space, that the Earth is already moving, and well, since the space is bent or curved or warped, then not only do material particles, right, like the Earth, which has mass, will be affected by it, but also other things like a beam of light, which even though it doesn't have mass, it's moving in a space that's been bent, and so it gives you the impression that there's a gravitational force on the beam of light. Three o'clock. So anyway, what I'll do next time, oh no, you have an exam. So let's do that lab after the exam. It'll be, it's one of those, all, Phys animations, simulation thing, and then, so we don't have to use equipment or anything, but I'll tell you about it. And then you do that, and then after we come back from Thanksgiving, after that, then we'll do that other lab that I wanted you to do with the measuring the spectrum of hydrogen atoms, excited hydrogen atoms. Okay, I shall see you. Have a nice evening, everyone.